Okay, what's the verdict on this one? So what are the absolute extreme values on the closed interval from A to B? Well, is it I guess, is it a closed interval? No, it's not, right? There are no endpoints there. So is there an absolute maximum?
No.
There's not, correct. Is there an absolute minimum?
Yes.
Where is it?
C2.
C2, good. Okay, what about this one? Oh, let's go back for a second. So now let's explain why your answer was consistent with the extreme value theorem. So if we scoot back and we go through the extreme value theorem, which I probably deleted that accidentally, it looks like I did, but I'll pull it up from the other day. Extreme value theorem. Where is that? There it is. There's the extreme value theorem, right? So let me copy that. So there's our extreme value theorem, right? If f is continuous on the closed interval from A to B, then that guarantees that f has both an absolute minimum and an absolute maximum on the interval. So what about this one that we just did? It didn't have an absolute maximum. What criterion did it fail to meet on the extreme value theorem? It's not a closed interval, right? Okay, what about this guy right here? Is it going to meet the extreme value theorem?
No.
How come? It's not continuous. So it doesn't guarantee there's going to be an absolute max and an absolute min. So is there an absolute minimum?
Yes.
Yeah, where is it?
A.
Is there an absolute maximum?
No.
No. Okay. How about that one? No, because it's open interval. Okay. So this one doesn't have an absolute min, it does have an absolute max though, right? If I filled in the endpoints, that one would work though, wouldn't it? Okay, even though it's got a sharp corner, it still is continuous, agreed? Okay, good. How about that one? No. Two problems. What if I filled in the endpoints? Obviously it's still got one other problem, not continuous. Does it have an absolute max or a min? No, good. Okay, so identify which of these graphs has a relative or local, same thing, a relative minimum value where f prime of A is equal to 0. So it's got to be a minimum. No, only one of them does. Which one of them has a local minimum where f prime of A is equal to 0? Okay, if you look closely at A, what's wrong with A? It's got a minimum at A relative minimum. It's kind of hard to see, but what's the shape of that one? It's kind of, it's a sharp corner, right? It goes from being a one slope to another one instantaneously, right? So it's not like it's a really exaggerated sharp corner. But it's not smooth, is it? Right? So where would you end up getting a relative minimum at A where A is a sharp corner? The derivative wouldn't equal 0. What would it be? Undefined. Okay, so if the derivative is equal to 0, that means horizontal tangent. So which one would it have to be? It has to be B, doesn't it? Because it's a smooth, right? We have a horizontal tangent there because it's a smooth minimum instead of a sharp minimum, right? Okay, so that one would be B. Right, here's why. It's going to be B because we've got a horizontal tangent there. Okay, how about this one? Where are we going to have a local minimum at B where f prime of B is undefined? It's going to be A, isn't it? Right? Because we got sharp corner. So it's A. You get the idea. Okay. All right, so how about this? So looking at this picture, the local minimum points local minima occur at which x values? Or local means relative. Different books, I pull these from a bunch of different online textbooks, you know, with interchangeable words, relative and local.
Q.
So Q, good. Q, where else? Not A though, right? Because what do we say? What's our convention going to be about endpoints? Can endpoints be relative extrema? We're saying no, right? So A is out of the question. So at Q we get a local minimum. Where else? At S, right? So that'd be Q and S. Local maximum points occur at P, R, I guess that's it, right? Absolute minimum points occur at A, that's it. Absolute maximum points occur at, well, that's a tough one. It looks like, yeah, I mean, I don't know which one's higher. I guess P, that's a bad question though. It's hard to see which one. It should be more obvious.
What would T be? Is that anything?
Nope. So T is nothing. T would end up being a false alarm, right? T is a place where if we found all the critical numbers, where critical numbers occur where what happens? Where the derivative is undefined or the derivative is zero. So this is a place, this would be a false alarm, wouldn't it? At T, we're going to get a horizontal tangent. So that is one of the critical numbers that we're going to uncover, but when we test it, we're going to find that it failed. It's not actually an extreme. It's what we'll later call an inflection point. Okay? All right. So let's go back to the example that we were working on the other day before yesterday, when we left off. So we were, the kind of the big math thing we're going to do in section, where are we in, 3.1, is finding absolute extrema on a closed interval. Okay? And what do we say about this? Well, the only places that absolute extrema could occur would be at peaks or valleys, right? Or endpoints, correct? Peaks and valleys all have to occur at critical numbers. So the easiest way to find all of the absolute extrema on an interval is just going to be to find all of the critical numbers between the endpoints. So on the open interval, we'll evaluate the function at each of those critical numbers. We'll evaluate the function at each endpoint, and then just compare. The biggest value is the absolute max, the smallest value is the absolute min, right? And we were looking at, I believe, this example, right? Here's where we left off. So I gave you a function. Here's f of x. Here's the closed interval on which we're analyzing this function, and we want to find all the absolute minima and maxima, right? So in order to do that, first thing is we got to find the critical numbers, which means we have to take a derivative. So first step was to evaluate the derivative, or to find the derivative, which we did. That's an easy one, right? It's just if we differentiate a polynomial, we just differentiate term by term, and we got 9x squared minus 6x minus 3. And so we're gonna find, based on that derivative, we're gonna find all of the critical numbers, both kinds. Where is the derivative undefined, and where does it equal 0? Well, this one's never undefined, right? No, there's no red flags on that one, so we can forget about those. But we do have to find out where it equals 0. So we set the derivative equal to 0, and we factored it and applied the zero product property, and we got the answers negative 1/3 and positive 1. Okay? So those are the places where the derivative is 0. Now let's look at our interval. Our interval is restricted to be from negative 1 to 0. So which, if any, of those fall in our interval? Negative 1/3. This one's outside our interval, right? So we could actually discard this one because it's not between our endpoints, right? So we only get one critical number we have to check, which is negative 1/3. So here's the part I want to show you. This is the part that's pretty handy. We can make a table out of this thing. So here's how our tables are going to look when we're doing functional analysis in calculus, which is what we're going to be doing all unit, or this all chapter, right? We're just going to make some rows. The first row is going to be x. And I'm just going to draw the x-axis up there. Okay. Next one is going to be y or f or whatever we're going to call it. I'll just call it y. And the next one is y prime. Okay. And that's our table. That's all we need. So on our table, we're trying to find absolute extrema on the closed interval from negative 1 to 0, right? So then we're going to do this. We're just going to, in the x row, we're going to represent, just like it's on the x-axis, we're going to represent the closed interval on which we're looking. And then all of the critical numbers that we uncover by using the first derivative, we'll put in the appropriate places in this row. Okay, so we only got one of them, which was negative 1/3. So those are the three x values that we needed to consider. And why did we consider this one? Because that one, when x equaled negative 1/3, that was a zero of our first derivative, right? So that's telling us, when I see those two things together, that's telling us that this is a first derivative critical number, right? So all we got to do when we're finding the absolute extrema is we're just going to look in row 2 and we're going to evaluate the function at those three places and just compare the results, right? So what is the value of our function at negative 1? Well, let's plug it in and see. If I let x equal negative 1, I'm going to get, what, negative 3 minus 3 plus 3 plus 2, so negative 1. Okay, so we end up with the point negative 1, negative 1, right? Now that looks just like an ordered pair, turned kind of sideways, right? But it's the ordered pair, negative 1, negative 1. How about when x is 0? Well, we get 2, right? So we get the point 0, 2. How about when it's negative 1/3? Well, that's a little trickier. What are we going to get? Negative, yikes. So we're going to get negative 1/9. Minus 1/3. Plus 1 plus 2. And so that's going to give us something, it's going to give us something greater than, would you agree it's going to be greater than negative 1 and less than, oh no, it's actually going to be bigger than 2, isn't it? So we're going to get, what is that? Yeah, so we're going to get, we get negative 1/9 minus 23/9. So we get 3 is 27/9 minus 4/9. 23/9, right? Or if we write it, so 23/9. Well, that's equal to, it's not roughly equal to, that's equal to, as a mixed number, that would be 2 4/9. 5/9? That should be 4.
18.
Oh, we did it wrong then, because it should be 4, shouldn't it? Oh, no, you're right, it's 5. Never mind, it's 5. Now, we don't use mixed numbers in calculus ever, but that's just handy for us to think of it as a mixed number, because then we can see that it is bigger than 2, right? So, based on that second row, what's our absolute extreme? What's our absolute maximum?
That.
It's that. The absolute maximum is 23/9, isn't it? And it occurs at x equals negative 1/3. What's our absolute minimum? Negative 1, right? Our absolute minimum is the minimum y value, which is negative 1, and it occurs at negative 1, at x equals negative 1. So when we fill in the blanks, (23/9) at x equals negative 1/3. Absolute minimum is a value of negative 1 at x equals negative 1. Right? You get the idea? Okay? Let's do another one. So how about one like this? Find the absolute extrema, if they exist, as well as all values of x where they occur. So here's our function. There's f of x. There's our closed interval. Okay? So what do we got to do first?
Take the derivative.
Take the derivative. Okay? So that's quotient rule, the dreaded quotient rule, right? So what's that give us?
4 minus x over 3 plus x, then we equal 1 over negative
Well, okay, but we follow the quotient rule. What's quotient rule?
I was reading that.
Low D high, oh, well, we can just do quotient. So low D high, 3 plus x, because they're going to be such easy derivatives, this won't be bad. What's D high? Good. Then we go minus, right? Minus high. What's D low? Divided by low squared. So what do we end up getting? If we distribute, we're going to get 3 minus x minus 4 plus x, right? So the x's cancel. So we get 3 minus 4 is -1 over 3 plus x squared. Did I do that right? Oh, you're right. So it should be -7, shouldn't it? Yeah. That comes out, -7. Okay? So there's our first derivative. Okay? So we got to find critical numbers. Critical numbers occur where the derivative is undefined and where it's equal to 0, right? So let's find those. F prime is undefined where? Where's the only value of x where that would be undefined? The bottom is 0. What would that be? X is equal to -3. Good. It's undefined at x equals -3. Where does this now? Where does this derivative equal 0? Or does it? So if we've got a function that's written in rational form where I've got a numerator and denominator, think about the behavior of a fraction. When does a fraction equal 0? When the top is 0, right? It's undefined where the bottom is 0. It equals 0 where the top is 0. Does that top ever equal 0? No. No, it's constant. It's -7. So f prime is 0 or equals 0 nowhere. Right? Okay, so what are our legitimate critical numbers then? We're only looking for critical numbers on the open interval between the endpoints. So are there any? Yeah, but that's at an endpoint, so technically it's not a critical number, right? It's an endpoint instead. So this is a really easy one. All we got to do now is just evaluate the function at the endpoints, and you know, guaranteed, that the minima, absolute minimum, and absolute maximum have to occur at the endpoints. Have to. Okay? And if we make our little table, it was 0 and 3, right?
Yeah.
So what's the value of our function at 0? 4/3?
Yeah.
Okay. Oh, I'm going to back up a second. So -3 isn't even an endpoint, is it?
No.
-3 is just outside of our interval, right? So either way, it doesn't count. It's not a critical number, right? We have no critical numbers. No critical numbers on the open interval from 0 to 3. So we'll just evaluate the function at both of those places. So I get 4/3 here. What do I get at x equals 3?
1/9.
1/9.
And that's a pretty.
So that's the maximum and that's the minimum. Absolute maximum and absolute minimum. Done. Okay? No other possibilities because there were no interior critical numbers. Okay, let's try another one.
It was 1/6, but it's still.
Oh, did I mess it up? Oh, you're right, 1/6.
But
Yep.
it's, doesn't matter.
I'll fix it just for the notes. Okay, and so we could summarize that by saying absolute max, absolute min, right? Okay, how about this guy? So there's our derivative. Let's find f prime. It's gonna be kind of nasty. So, what do we do?
You get 24 and 11 divided by 13.
So,
X.
264.
264 divided by
264 thirteenths, x to what power?
13. X to negative 213.
Everybody see that? Because we gotta take we're gonna take the exponent down front and subtract one from the exponent, right? So negative 2/3 plus 264 over 13, x to the what? Eleven thirds. Okay? Right? So now, there's our derivative. We want to put this in a form, and this is real important, we want to put this in a form where we can find the critical numbers. Did I make a mistake?
Isn't it 2 over 13 and 11 over 13?
Oh, yeah, 13. Whoops. Yeah, there we go, sorry. Okay, so we want to put this in a form where we can find the zeros of the derivative and where the derivative is undefined. Okay, that's not a very good form, is it? Now, what worked out really well in that last example, you guys told me the answers really easily because we had it written as a ratio, right? So that's a good thing. If we can take our derivatives and we can write them in rational form, then it's easy for us to find the critical numbers because they're just going to be the zeros of the numerator and the zeros of the denominator, right? That's really handy. So let's do that here. What's that look like?
We're going to do negative.
Right, okay, so we got negative exponents. Why don't we do this? This is something, we've seen something like this previously. You have two options. You could just write these both as fractions and get a common denominator, right? But what we did in the past is we always tried to factor out the greatest common factor, right? The least common power of all the exponents. So we could factor out a 264 over 13. What power of x could we factor out? It's got to be the least power of x. So a negative 2/3, right?
13.
I keep saying thirds. Negative 2/13. What was that? I did that once before earlier. I could not. Kept saying the wrong thing about 20 times. Okay, so we're going to factor out 264 over 13 times x to the negative 2/13. And what's left behind?
X.
Well, that's just going to be 1, right? We factored everything out. And then how about this one? If I undistribute, well, the 264 over 13 is gone, but what about the x to the negative 2/13, right? If I'm going to divide away an x to the negative 2/13, what's left behind?
That's 14.
No,
13.
13/13, right? See what I'm saying? Because we're going to say, if I'm dividing that away, I'm saying x to the 11/13 minus negative 2/13 is 13/13, right? So let's write that down. So x to the 11/13 divided by x to the negative 2/13 equals x to the 13/13, which is x, right? Everybody see that? Rick's here.
You don't need that.
Okay, so Katie, how can I write that then as one big fraction? So I've got a fraction out here. We already know the 264 goes on the top, the 13 goes on the bottom. 1 plus x goes top or bottom? Top, it's already on the top. What goes on the bottom? To x to the 2/13, because it's a negative exponent. Okay? That's handy to write it that way, because now we got a top and a bottom to our function. So we can find the two types of critical numbers really easily. Once we get it written in rational form, we know that where is this derivative going to equal 0? When x equals what? Remember, a fraction equals 0 when the top is 0, right? So we know that f prime equals 0 when the top, and really we don't care about the constant, we just care about that factor, don't we, right? When 1 plus x equals 0, so x equals negative 1, good. F prime is undefined. When the bottom, which is x to the 2/13 equals 0, so x is 0, right? So those are our two species of critical numbers. Are those both on our domain? Yeah, they are, right? Both 0 and negative 1 are on our domain. So this is a little more exciting one. Now we can actually make a table that means something. Okay, so we want to enclose our domain on our table. We're going from negative 2 to 1. Is that what it was? Negative 2 to 1. And the interior critical numbers were negative 1 and 0. So those would look like that maybe, right? Okay, what do I put in the first derivative row that corresponds? How do we know, how do we communicate here very clearly on the table that those are critical numbers? What happened at negative 1? 0. Yeah, the derivative equals 0, right? What happened at 0? Undefined. So the first derivative was undefined, right? So that's telling us right there that those are critical numbers. See how the table works? It's nice. Not that that's such a big deal now, but when we get into the optimization stuff, we're going to go a lot further with the table. We're going to add another row to it, and we can do a ton with this table. We can put horizontal asymptotes on the table. We can put vertical asymptotes on the table. We can represent everything on this table. This table's awesome. So then all we have to do now is just compare the values of the function. What was our function again? I'm going to take a picture. I don't want to keep scrolling up. Okay, so there's our function. So if we evaluate each of these, evaluate the function at each value of x, what are we getting? So at negative 2, oh my gosh. So we do that, let's just make it a decimal. What is 24 times negative 2 to the 11/13 plus 11 times negative 2 to the 24/13? Desmos to the rescue. Okay, so, goodness. Okay, so if we do that, look on Desmos, we can make this really easy. Desmos is so handy. Let's define the function. Everybody see what I'm going to do here? If I define the function as 24x to the 11/13 plus 11x to the 24/13, then all I've got to do, I can use Desmos and just go f of negative 2, and I get that, right? It is a big number. But, so we'll just round to, how about two places? So negative 3.6. Oh. Okay. Let's plug in negative 1. And we get negative 13. If we plug in 0, what are we going to get? 0. That one's easy. And if we plug in 1, we're going to get 25 or 35. Right? 1 to any power, just going to be 1, right? So what's our relative minimum? Or absolute minimum, sorry. What's the smallest value the function could ever have on that interval?
Negative.
Okay, negative 13 at the x value, negative 1, right? So the absolute minimum of the function is negative 13, which occurs at x equals negative 1. What's the absolute maximum of the function? 35, which occurs at positive 1. Okay? Does that make sense? Okay, so make sense? You get any idea? Okay, I don't know, we can do more, but maybe that's enough.
Maybe it's too close, it's too quick.
Yeah. We'll call it. We'll do a couple more. When we come back next time, we'll do a couple more after the long weekend. But that's enough for this time. If you want to, go ahead and do some work for 10 minutes. Get questions answered. Sure, that's good. Yeah. If you got